One of the most common instruments of the day are the string instruments such as the guitar. The string's properties govern its eigenfrequencies, which in turn govern the sound it produces. In this product, the string's properties and eigenmodes are analyzed in order to determine how the frequencies depend on the way the string is plucked. Initially, guitar is used and the string is plucked in several different locations. This is recorded and analyzed with an FFT program in order to determine the different frequencies that make up this sound. The string that is analyzed in this project is the A string of a standard tuned guitar. Its corresponding natural frequency is 110 Hz. We are only interested in the 4 lowest eigenmodes. This is sufficient to analyze and understand the phenomena we are looking at. By plucking very close to a node in a specific mode shape, different frequencies will be excited depending on the position. This difference is perfectly audible and is used by musicians all over the world. The difference can be seen when looking at an FFT. To obtain an FFT, one simply have to record the sound of the guitar when plucked at different locations. The recorded audio is passed through a fast Fourier transform, and we can now observe the dominating frequencies for that audio. This is the FFT from the first eigenmode. If the guitar is tuned right, we should see a peak at 110 Hz. Looking closely, this is exactly what we see. Some may also notice the absence of overtones. This is because we excite the string in its very middle. Looking at this picture of the different modes, it is clear that if plucked in the middle, mode 2 and 4 is not excited. This is because the location of the impulse from the pluck is the same location as the node in mode 2 and 4. For subsequent plucks, the same holds. As we excite at different locations, we see other dominating frequencies. It is now of interest if we can recreate this phenomena in a computer model and compare the results. In reality, a guitar string consists of a circular centroid with a wound string around it. This is very difficult to model, so we simplify the string with a solid circular cross-section. The dimensions and properties are based on industry standard. An utmost paramount detail easily forgotten is that the string is tuned. To account for this, the string can be imagined to lay on 2 supports. One support allows for horizontal movement. At this support, we apply a load to tune the string. This will tension the string, just as it would when turning the tuning knob at the end of the guitar's neck. This force is based on the side frequency and the mass of the string. To check the tuning, we perform a frequency analysis to ensure satisfactory tuning is obtained. The pluck is represented by an impulse load. This impulse is placed at predetermined locations along the string in order to excite different eigenmodes, just like the real guitar before. However, a computer model of a string does not produce any real sound, but we can use the displacement over time to obtain an FFT. However, the choice of measuring point is paramount. It cannot be a point which coincides with a node from an eigenmode as described before. Thus, we extract 3 different measurements at strategic locations to ensure the complete frequency spectrum is captured. Sound sounds different at different locations. For instance, a small room. In example, your bedroom makes a guitar sound rather warm and tight due to the textiles damping the sound. However, inside a very large cave with hard surfaces, the sound is more washed and echoic, due to reverberation time among many other things. This is why a bathroom, similar to a cave with its hard surfaces, is the preferred location for the amateur vocalist. But how is the quality of the guitar's sound affected? This is a difficult thing to measure accurately, as everyone have a favorite sound of the guitar. Many even use reverb and echo as an effects when playing. However, a room can be measured in terms of intelligibility. Thus, let's say that this translates to music. Is it more or less difficult to distinguish individual notes in different types of acoustical rooms? Here is a sound of the guitar played in a bedroom. And here is the same melody inside a bathroom. The small difference lays in the reverberation time. This is the time it takes for a sound to be reduced by 60 decibels. This time is longer inside a room with hard walls such as the bathroom. Thus, the sound is slightly more washed and not as tight as in the bedroom. Wrapping things up, the results from the recordings coincide with the results from the computer model? Well, both the model and the guitar show the same frequency composition and the dominating frequencies coincides with each other. This was the expected result, and it validates the computer model. In this short video, we've looked at the properties of a guitar string and its behavior when plucked at different locations along its length. Plucking at different locations excite different modes, resulting in a different frequency composition and a different sound. This is a well-known phenomenon and is the foundation of music theory.